Thank Gadi for inviting me, and I'm going to talk on two-photon laser, or in fact more towards a two-photon laser, because we are on the verge of getting a laser. It's not lasing, but I'm going to talk about the concept of this novel semiconductor laser. And before starting, of course, I want to acknowledge the excellent team that made all the two-photon laser or the two-photon emitters possible. Alex Hayat, Pavel Ginsburg, Amir Nevet, and Nikolai Berkovich from my group, all graduate students, PhD students, and Andrea Peer did many of the devices that I'm going to talk about, and some funding. Before starting the talk, I just want to pay tribute in one slide for the 50th anniversary of the laser, and remind you that the first laser actually realized by Theodore Nyman at 1960 in May, and in fact the work was rejected because lack of novelty, and he couldn't publish it. And later on, semiconductor lasers appeared 2 years after: gallium arsenide phosphide, visible laser, near-infrared laser, and in fact these two materials we used to make our novel emitters using two photons. And the real semiconductor laser, continuous at room temperature, should be 10 years later, so it's 40th anniversary for the semiconductor laser that is really working at Bell Labs. So this is just for sake of history, and then we are going to the talk. And what I'm going to talk is, first of all, explain all of you what are the concept of two-photon emitters, both spontaneous emitters and later on stimulated emitters, or gain, medium, or lasers. I'm going to explain why this type of lasers are important and what we can do with them. And then I'll talk to actual measurement of two-photon emission from semiconductor materials and show our progress towards getting really actually a laser out of this type of quantum process. And I'll talk about enhancement of this type of emission, of the two-photon emission, by nanocavities. It's very important to enhance this emission because it's quite low in intensity, and I'll talk about engaging the two-photon emission with nanocavities. So basically, just two bands in semiconductor, conduction band, valence band, and the regular emission, either LED or laser, is performed by injecting electrons, exciting electrons, relaxation of electrons, which generates an equivalent of four-level system in laser, and electrons or holes are recombined with emission of photon. This is the regular LED and laser that we are getting in semiconductors, and the question is how we can get something else out of this. So basically, if we have this, for example, green pointer, if the light would come from a semiconductor green laser, which I doubt that it is. I think that it's now just multiplication of a red laser. However, if it was a semiconductor laser emitting in green, and I put a green filter here, so basically what you see now that coming from this semiconductor laser is a stream of pairs of photons with colors starting from green, red, infrared, far infrared. Basically, from each transition like this, you can get also a transition of second-order process, which means that two photons are emitted from this transition, as I'll show you schematically here. Again, the same electrons are excited, and there is a probability for the process of this emission of pairs of photons. Again, this is not a surprise. Everybody who took a second course in quantum mechanics know that when you excite a level system with electromagnetic radiation, of course, the first order transition is a single photon transition, and of course, you can get higher order transition, which is the two photon transition. Mysteriously enough for me, nobody did any type of measurement, even theory, on this subject in condensed matter. solid state in semiconductor. Only demonstration and discussion about this were in atomic system. So about 2.5 years ago, we made the first measurement of actual two-photon emission from solid state, in this case, semiconductor. What is very important here that any two photons that are complementing the energy to the transition energy, the gap energy, can be emitted. So again, the gain bandwidth or the emission bandwidth is huge. It's not determined by the material, it's just determined by the band gap and the quantum process of the two-photon emission, because almost zero energy photon and almost gap energy photon can be emitted and all other combinations. So basically you get huge homogeneous emission, and of course this is very important because if you don't have limitation of the material on this bandwidth, you can make very short pulses, large tunability, and so on. So this is one of the main features of this type of laser. Also, it's a second-order process, which means it's weak. It's weak by about 4 orders of magnitude compared to the regular emission of 4 or 5. So we cannot get, let's say, more than microwatts, but we have very large tunability. You have two-photon emission, which is important because of the quantum nature of this. So you can get this for application. Okay, I'm not going to dwell on too many mechanisms explaining why this emission is possible. Again, it's quite known for anyone who did some second-order perturbation. Basically, one can talk about a virtual state. So the transition from here to the valence band is via some virtual state. There are no real states in the gap. And what is important, I'm going to dwell half a minute about this equation. This is the rate, how many photons are generated per unit of time, which is proportional to the matrix element, the strength of this transition, which I'll just write in a minute, and the density of states of the optical mode. And in fact, it's the density of states of the two photons multiplied. Density of states, of course, are very important, as I'll show later on, because when you have a material, the only way to change, to enhance, to improve the emission is by playing in optical structures that are increasing the number of available electromagnetic modes in order to emit the photons into them. So these are the density of states. I'm going to talk about this when I talk about nanocavities. And again, not dwelling on the exact terms that are quite known, exact terms from the second-order perturbation showing the transitions. What is important that there is still no complete model for the spontaneous two-photon emission, the full quantum mechanical modeling of the semiconductor with two vacuum fields of the optical modes in order to get exact rate equations or exact rates. So there is still no lack of such a model. We have a partial model published in this paper. Okay, so second question before going to more details of the devices that we are doing, why we need these two-photon emitters. I made some clues before, but I'll divide it now to two emitters, LED type or spontaneous emitters. In this case, of course, since we are emitting two photons that are correlated, they are generated at the same time, and they are correlated. Of course, this is very important for quantum information, quantum computing, because if you want to send a photon state, you can measure one of the photons that you are generating, and then you know that the second photon is in your communication channel. Basically, they are even not only correlated, they are entangled, because you cannot know which of the two photons having the larger energy or the smaller energy, you just know the sum of them. So they are energy time entangled, so it can go to even to more sophisticated application in communications, in quantum computing. But in addition, you can use them for many other applications, for sensing, for example, because first of all, you have a source for mid-infrared photons. If you just take an indium phosphide-based laser and you use the second transition, then basically you get very broad infrared emission, which is centered about 3 micrometers. It's very difficult to find very cheap and small sources at this regime. Of course, the fact that you are emitting correlated photons can assist or increasing the signal-to-noise ratio in sensing applications. Okay, so basically, these are some samples of application of an LED. And for a laser, this is just I'm not going to dwell on this type of application of entangled sources. However, energy, time entanglement can be produced from this source in a cavity, and we have few papers about this and variations of this. What I'm going to dwell more is going to lasing and gain. And when you have such a material with huge bandwidth, of course, you can expect to get from a semiconductor a very, very short pulse, which is not feasible in any other type of semiconductor gain or amplifier. Basically, since you have such broadband gain, you can get pulses as short as few optical cycles, just a semiconductor. And we made in this case, not experiment yet, but very detailed calculation taking in account all nonlinearities in the material, showing really that you can get this type of compression. Of course, you have very large bandwidth. You can tune easily during this bandwidth. You can get, since the emission is not linear, you are emitting using two fields, then you can have squeezing due to the nonlinearity of the emission. And basically, there are more applications, but these are the most important ones. Again, nobody did a solid state or semiconductor laser or emitter like this. Only reports were on atomic system with very complex high Q microwave cavities or cavities with atom injection. And it was shown basically that such lasers are feasible in single atoms. The only theoretical mentioned this possibility of compressing such pulses in semiconductor two-photon emitters was by Orenstein many years ago. Okay, demonstrating the compression issue. Again, since the gain is nonlinear, it depends on the intensity. Of course, you can expect that as the pulse propagating in the structure has higher peak pulse, it's going to be enhanced, or the gain will be larger here, so pulse will be narrowed until all the carriers from the semiconductor will be depleted. Then, of course, we have some simulation. This is blue is the pulse with the optical oscillations, propagating in really with all effects, nonlinear effects of semiconductors, and collapsing to few cycles. This is becoming shorter and shorter, and this is collapsing to very few cycles. And this is a view of this after propagation for some distance in the waveguide, and showing, in the bulk, this is bulk gallium arsenide, showing very few optical cycles. These are intensity cycles, so basically it can be compressed to about 2 optical cycles, which mean few femtoseconds. We are now getting to the measurement, in fact, showing such devices that are working basically on the same material that make regular emitters, or LEDs and lasers. And in fact, what is important is that it's very general. Each material that you have a first order transition, there is no reason why you don't have a second order or two-photon transition. So basically, we're going to talk about this spontaneous emission. Again, two-photon spontaneous emission. What is the second process is singly stimulated two-photon emission. So you are sending from the outside one photon. It is stimulating this transition, while the second is spontaneous. And this is more of the laser type. You are sending a pair of photons, and you are generating multiplication of this pair in order to get gain, or eventually also lasing. And basically, when you are making this structure, filtering very good the first order transition, and measuring in all the spectrum that we can measure, limited by our measurement system, get very, very flat emission all over the area. We get white photons. I mean, each photon that is emitted is very, very broad band. And of course, there are questions if this emission can be a result of some impurities or some other mechanisms. And we showed systematically that there are no such impurities. And the way to show it is that basically this emission is homogeneously broadened, and there is a connection between the two photons. If one photon is excited here, basically the second one should have some signature of the second one. So what is done here is the single stimulated emission. We are sending one photon. It is amplified by this transition and generating, of course, the second one. This is the basic spontaneous emission. And now we are sending a CW photon in this wavelength. And what you see that the second one is generated and it's amplified. It's above the spontaneous level. Increasing this intensity increases the complementary wavelengths. Again, these two energies are complementing by the E gap of the transition. And again, furthermore, what is very important that it's not only that this is amplified, but the whole spectrum, which is not interacting, is reduced, which means that the spectrum is homogeneously broadened. All the spectrum is of a single spectrum, of a single photon. It's not that there are some photons of this energy and of this energy. There are single ones, so if you amplify this, all the spectrum should go down. Okay, and this was the first experiment in bulk gallium arsenide. Second one was in quantum well structures, red emitting laser. Again, basically the same results, very broad emission in double the wavelengths, centered about double the wavelengths. And we got also this nonlinear effect of the connection between these two photons, also for this quantum well structure. And recently, Yelena from Berkeley showed also that in quantum dots you can get such an emission. So basically, we get such an emission from bulk, quantum wells, quantum dots. Again, there is no limitation to the type of the source. Okay, I'm not going to dwell about correlation because, again, to make a correlation, you should prove that the two photons are generated at the same time. This is a type of correlation that you should say that if one photon arrives to a detector, one detector, the second one should arrive at the same time. Since the bandwidth is so huge, the time scale that we should look for is femtoseconds, few optical cycles. And there is no way to measure such a correlation, this wavelengths, as I know of. Maybe if someone comes with a very sophisticated system, I'll be happy. So basically, we have correlation in any time scale that we are choosing, but we are far away from showing that really there are two photons are emitted at the scale of few femtoseconds. We saw just a second ago that there is a spontaneous emission of photon pairs. We saw that we can have singly stimulated emission. We are sending one photon from the outside. It is amplified, and it forces the second complementary photon to be amplified as well. Or in fact, it was stimulated emission. And now we are going towards lasing. The first step towards lasing is achieving what is called in the field of semiconductor laser transparency, in regular laser population inversion. So basically, you want to see that if you take a structure and input pairs of photons, and the pairs of photons are, of course, usually absorbed if you don't excite the semiconductor. And then you excite the semiconductor by current, increase the current until the two photons are going through as if the material is transparent. And of course, if you excite further the carriers, then inverse process of stimulated emission will occur. So first of all, we want to see that we can get to this level of two-photon transparency. And we made an experiment. We sent two photons at the same frequency, about the half of the band gap, and sent them to the LED or amplifier structure. The first one was quantum well-based, and we injected current and measured to see if really we're getting the transparency. We measured it not directly, but by monitoring the single photon emission, the regular red or infrared light that is emitted from this structure by the excitation to see when it changes from increasing to decreasing with the optical pulse that we injected. So basically, it's quite complicated scenario. The only thing that I would like to mention here is that we have in such high input pulse, and we need high input pulse because all our gain is nonlinear. You have to have high input pulse in order to get enough gain. You get nonlinear effect as second harmonic generation, and one linear effect, which is very important, called free carrier absorption. The electrons are on the conduction band, can absorb this photon, and it happens always also with regular lasers. However, since two-photon transition is weak, this is maybe a dominant effect. Basically, you have this square term, which is the gain or two-photon gain or two-photon loss, and this is a regular free carrier absorption loss, which is linear. Okay, after dwelling with these results, and I'm not going to show you in detail how the signature that we are taking in an experiment, after signal processing, this is the intensity squared of the input optical pulse at half band gap, and this is the luminescence that we are monitoring from the conduction band, the first single photon luminescence, in order to see how we are doing with the absorption. So, and we are increasing the electrical pumping or the excitation of electrons. Basically, what we achieve about at 14, 15 milliamps is that the slope is becoming zero, which means that we are not getting any luminescence, extra luminescence due to the two-photon absorption, which means that here we are stopping the absorption, and here we have a transparency. This is with zero current. This is a regular two-photon absorption coefficient. Okay, so we get transparency. The second stage, to get a lasing, of course, you have to get gain. And we found out that in this structure, the previous structure, quantum well structure, we cannot measure directly the output, the gain. We cannot input an optical signal and measure it amplified at the end, because the overlap of the mode with the quantum well is quite small, and we have a lot of overlap with the losses. So we changed the structure to a bulk laser, which is not as modern, but however, for this purposes is much more appropriate, with very large confinement of the mode into the active medium. In this structure, we are able to demonstrate really an output. We send, again, a pulse. This is the intensity of the pulse, and we monitor the output signal, and we got at a pumping level of zero, which means that with no current into the structure, of course, the pulse is generating a two-photon absorption, and this is the slope. A transparency, which was about 12 milliamps or something like this, 40 milliamps. We got transparency, and we get amplification, increase of the output due to the input pulse is a square with this slope. It's very nice that you can get amplification coefficient much larger than the absorption coefficient, which is not doable with regular linear amplification, but I'm not going to dwell on this. So to complement this experiment as a starting of understanding of propagation of or compression of pulses in such a gain medium, we measured also the spectral modification of the pulse as it propagates in the medium, in the gain, in the loss or two-photon absorption regime, and in the gain regime, and showing, in fact, distinct spectral modification, which means that we are getting some of the feature that we would like to get later on for the compression of the pulse. Compression of the pulse is a more complicated experiment which we have to measure really in the time domain to see the huge compression, and we are in the process of doing such an experiment. Okay, just to show you that we are not far from lasing. From our experiments and extraction of coefficients, what we get is this is the coefficient of the free carrier absorption, 16 to the centimeter to the -1. However, the nonlinear gain, which is gamma 2, which is material dependent, and I is the input intensity that we could achieve with the current system, is at the same order of magnitude. It's a little bit smaller, but it's not 1 or 2 order of magnitude smaller. Just to give you the numbers, of course, in the regular semiconductor laser, the first order gain in the order of 100 can go to 1,000 centimeter to -1. However, we are very close to get gain larger than the loss, which is the condition of getting, of course, a laser. But not yet, very close. In the last minutes, I'm going to talk about the enhancement of this phenomenon. As I told you, the phenomena is weak. To get high-efficient sources, you would like to enhance the interaction, and I'll talk a little bit about enhancement of this interaction by nanocavities. And again, I can go to details in the calculation and show you, but I'm going to just to talk very briefly without any calculation, just schematically. Basically, there are two mechanisms of enhancing the spontaneous emission, or LED-like operation of any photonic emitters. In the spectral domain, you can take the density of states, available modes of electromagnetic modes that photon can be emitted to from just the regular states of free space, and squeeze at a specific wavelength the density of state to be much larger. This can be done with cavities. This is done with dielectric cavities in optics. Just a few examples. Photonic crystals, torus, many of them, Fabry-Perot. The main issue here that what you are doing is you should have very high quality of confinement of the light into the structure in order to make this delta function like density of states. However, what you are not gaining here is the volume of the cavity, the volume of the electrical field of the photon is quite large. It cannot go below about 1 wavelength cubed. Okay, so the second way to increase it is by squeezing the size of the photon. If spontaneous emission, in my favorite interpretation of it, the atom or the semiconductor start to emit a virtual photon, and this field is making back reaction, back radiation on the atom, boost it to further emit. If the volume of the photon is very large, then the field that the atom experiences from its own emission is very small. But however, if you squeeze the field such that when atom starts, the field is kept near the atom, it boosts itself and enhances the emission rate. So basically, if you reduce the size of the photon, very small sizes, then you can have enhancement. And in fact, this is a way that we are using, because in our case, the emission is very broad. So if you just gain by squeezing the density of state to a very high value to a single wavelength, it's not going to help you. So what we are going to do is to squeeze the size of the photon, and the only way to do it, to squeeze the size of the photon in size much smaller than the wavelengths, is what is called by nanocavities or plasmonics. Okay, so basically, you take plasmonics, metal particles, you make many structures, and this is a model volume of the photon volume in lambda cube units. So basically, you get much smaller than you expect from any dielectric structure due to the plasmonic effect. And the Q factor is small. You get a lot of losses, but it's very important for us to get very low Q because you want to enhance very broadband. So this is a very good combination, and just finishing soon showing first experiments. What we get is bulk emitter based on semiconductor, and what we are doing is generating very small cavities. These are nanometer scale cavities or antennas by depositing gold with various shapes in order that this will localize the light to the size of nanometers, of 10 nanometers, at specific wavelengths. Designing this to be at a specific wavelength, and this is, for example, the resonance of this structure. This is wavelengths, this is a transmission. So basically what we get is very broad resonance as we expect from the low Q, however, very distinct resonance. When you apply this resonance, which means that at this wavelengths, the field is localized near the particle, and you have much larger or photon, or much smaller photon volume. And when you are looking at the emission was completely flat. Now, of course, the emission is enhanced, first of all, compared to the regular emission, the two-photon emission, by a factor of 20 in this case. And of course, it has some spectral shape. This spectral shape should be symmetric from the other side. However, it is quite difficult to measure single photon level at this range. Okay, so basically, summarizing it, we have two photon emitters, which are LED-like. We are approaching a laser, and we know how to enhance emission by adding to it nanocavities.